Hello everyone, my name is Wenjun. I'm honored here to report our recent work on realizing an entanglement-based multi-user quantum network with integrated photonics. This is the outline of my report. I will first introduce the motivations of our research, and then introduce our specific work. In 2018, Soren and his collaborators proposed and demonstrated a fully connected network architecture. They developed a source of polarization-entangled photon pair source at telecommunications wavelengths, which has a bandwidth of about 60 nanometers. The spectra of the signal and other photons was then carved into 6 pairs of frequency-correlated channels. Ultimately, the source distributed 6 pairs of polarization entanglement photons between 4 users. Then in 2020, the architecture is further optimized and the resource consumption is further reduced to ON, making it possible to distribute 8 entangled states among 8 users using only 16 wavelength channels and additional beam splitters. This fully connected network architecture are innovative and promising. How can we improve the hardware? In these pioneer studies, each pair of users share a bipartite entanglement through carving the signal at the spectrum into a series of slices, which may cause the loss of the brightness. We can use sources with broadband phase matching range and discrete frequency modes as an alternative. For a scalable quantum network, it is necessary to include quantum memories, which rely on narrowband optical transitions. The use of source with narrow bandwidth in individual frequency modes can also make it compatible with quantum memories. Moreover, one would like to have a stable, alignment-free, with scalable production solution for such sources in practice. By taking advantage of advances in CMOS manufacturing technology, integrated quantum photonics is a promising approach. Based on the above reasons, we think quantum optical microcombs is a good solution. Therefore, we choose to use an integrated silicon nitride microring resonator to generate energy-time entanglement photon pairs for the realization of an entanglement-based multi-user quantum network. Here is our photon pair source part. A continuous wave laser at the middle of the ATU channel 35 pumps the microring resonator. We use a fiber polarization controller to adjust the pump's polarization, and pump cleaning filters to remove unwanted spectral noise before injecting the pump into the chip. The microring resonator has a diameter of 460 microns and is evanescently coupled to a single bus waveguide via a 300 nanometers gap. Both the ring and the waveguide has a cross-section of 1,600 nanometers wide and 800 nanometers high. Light is coupled into and out from the chip by lens-tapered fibers, which are mounted on high-precision positioning mounts. The total insertion loss of the chip is about 5 dB, including both input-output coupling loss and the propagation loss in the bus waveguide. To characterize the microring resonator, we measure the transmission spectra ranging from 1.5 microns to 1.6 microns. The inside shows the zoom-in view of a resonant mode around the pump wavelength with a full width at half maximum about 615 MHz. The red figure shows the free spectral range and the quality factors of a resonant mode. We obtained 128 resonance mode and the average free spectral range is about 97.8 GHz, which is sufficiently close to the standard 100 GHz dense wavelength division multiplexer, and offers a plentiful selection of possible photon pairs at the telecom band. The average measured Q factor is about 300,000. Frequency-correlated photons are generated from the integrated nonlinear microresonator. The broadband phase matching, spontaneous four-wave mixing enabled by the device, combined with the cavity resonance, leads to the generation of correlated signal and other photon pairs that are symmetrically distributed to the pump laser. The spectra of the entangled photon pairs covers multiple resonances, and yet a frequency comb structure with the spacing given by the free spectral range of the microresonator. The right figure shows the spectra of the single photons emitted from our microresonator, measured with a reconfigurable optical processor and a superconducting nanowire single photon detector. Owing to the low anomalous dispersion of the microresonator, we obtain the single photon spectra covering the entire C-band, which is only limited by our spectrometer. The pump wavelength is highlighted in black, and the selected 12 frequency modes employed in experiments are color-coded with purple and yellow. We then measure the dependence of the coincidence on pump power for all 6 photon pairs. The generation rate of photon pairs shows a quadratic behavior with increasing pump power, which confirms the correlated photons are generated from the spontaneous wave mixing process. The difference in counts for different pairs arises from different losses of different channels. An instance of the histogram of the channel pairs is shown in the inside with a time tag unit. The peak represents the time correlation of the signal at the pairs, and a high signal-to-noise ratio of about 88. We fit the coincidence peak and extract the biphoton coherence time of about 300 picoseconds. The coherence time and brightness state of other photon pairs are shown in the table below. The data shows that the bandwidth is less than 600 MHz, which proves that we have obtained individual frequency modes with narrow bandwidth. Here, the average loss experienced by each frequency channel is measured about 8.6 dB. The selected 6 pairs of entangled photons are then allocated to users to form a fully connected network by an array waveguide grating and multiple dense wavelength division multiplexer with 100 GHz spacing. These 6 pairs of photons are then distributed to 4 users, respectively. Each user now receives 3 channels, thus sharing a different entangled state with every other user. Here we use different colors to distinguish different channel pairs. The quantum correlation layer, physical layer, and the wavelength allocation are shown on the right. Polarization coding is a commonly used coding method. The main advantage of polarization entanglement is that polarization is easy to manipulate and analyses are simple and efficient. It is therefore relatively easy to obtain high contrast. However, polarization is not robust enough to avoid decoherence in optic fibers, making it challenging for fiber transfer. Meanwhile, energy time encoding doesn't suffer from random polarization rotation in fibers, and it can transmit high-dimension bits. We use phase coding in our experiment. As shown in the figure, the frequency-correlated photon pairs are sent to 2 users. Each user has an identical and balanced fluorescent interferometer, and the output of the interferometer is connected to a single photon detector. Looking at the detection time at each user's end, 3 different values are possible. The first peak is due to the signal photon having taken the short path while the other photon takes the long path. The last peak is opposite. The middle peak corresponds to the indistinguishable event, in which both photons travel along the long or the short path. Conditionally detection only on the central time peak. One observes two photon interference that depends on the sum of the relative phases in two users' interferometers. In our experiment, each user receives the 3-channel and shares an entanglement state with every other user in the network by the multiplexing and demultiplexing techniques. The analysis and the detection module had by every user consists of a Francian interferometer with a time difference between two arms of 2.5 nanoseconds and a superconducting nanowire single photon detector. Note that the biphoton coherence time is much smaller than the path difference, effectively prevents the first-order interference in Francian interferometer. Now there are 6 combinations among 4 users. One way to distinguish the channel is to implement frequency-resolved detection at each user's detection module, which will drastically increase the complexity of the setup for each user. Instead, we harness the temporal degree of freedom. We add different optical fiber delays to each user. By doing so, we can identify different combinations of users by relative arrival times. Here for demonstration, we set the time interval between different pairs of users to about 10 nanoseconds. To verify the feasibility of the network, we measure the 2 photon coincidence for 2 phase settings, 0 and pi, respectively. Each coincidence histogram has 3 peaks, revealing 3 relative arrival times due to the intrinsic nature of the Francian interferometers. Here we can see the coincidence of central peaks vary remarkably between close to 0 count and close to 4 times of the set peaks, where the set peaks have heights that are independent of phase. The path difference is much smaller than pump coherence time, which can lead to the photon being energy time entangled. This condition is fulfilled in our experiment, since we use a CW pump laser with high coherence. Further, we measure the 2 photon interference fringe in a 30-second interval by post-selecting each peak. The results are shown in the figure as a function of the sum of the relative phases for both central and set peaks in the coincidence histograms. One can see clearly that the central peaks oscillates sinusoidally with the phase, and no interference can be observed for the set peaks. From the fitting, we extract the low and net visibilities. All the low visibilities are above 85%, which are greater than the classical band required for the violation of the bias inequality. After subtracting the measured accidental coincidence, the net visibilities are found to be above 96% on all pairs of users, proving entanglement in our fully connected quantum network. The detected brightness, including all the insertion losses of all components, is defined as the detected photon pairs rate per milliwatt squared per megahertz. In our work, the detected brightness of our source is summarized in the table. The brightness of the macroine is proportional to the third power of the Q factor, and the use of a macroine with a high Q factor will significantly increase the brightness. In conclusion, we developed an energy-time entanglement-based dense wavelength division multiplexed network based on an integrated silicon nitride macroine resonator, which offers a wide frequency span and a narrow bandwidth modes. 6 pairs of photons are selected to form a fully connected 4-user quantum network. The observed quantum interference visibilities are well above the classical limits among all users. and our result paves the way for realizing large-scale quantum network with integrated photonics architecture. Finally, thank you all for your listening.